Okay, so with this lecture, we begin the next topic, namely partial differential equations. So there's a number of sources we will dip into and extract inspiration from. So one of the books which I really like is a sort of an exhaustive treatment by K. Shankara Rao. So it's called, I think, Introduction to Partial Differential Equations. There is also one chapter in Ghatak Chua and another co-worker's textbook on mathematical physics. Then there is also Joglekar's book we might dip into for some parts. Then there is Balakrishnan's book, also has some useful perspectives to offer. Then of course we have books by Boas and Arfken, right? So we will dip into many sources, but in this lecture we will start with a classification of, we're primarily going to be interested in second order PDEs, because that's where the attention in physics is largely focused on. And so of course problems in their most natural form when they arise in a physics application are generally partial differential equations. We studied ordinary differential equations in great detail in the previous version of this course. And so, but really in problems have their origin in which have their origin in physics applications are usually partial differential equations in nature. And then it certainly, from a theoretical point of view, it helps to have a solid understanding of ODEs before we embark on our study of PDEs. So in this lecture we'll sort of set up the scene for second order PDEs and how there is this very useful classification for them. Okay, so partial differential equations, as I'm sure we all know, are differential equations in which there are partial derivatives involved, right? So there's at least two independent variables and partial derivatives are involved. So the order of a partial differential equation is of course somewhat similar to the idea of the order of an ordinary differential equation, and it's given by the order of the highest derivative occurring in the equation. So I've cooked up this partial differential equation. So x squared times the second order partial derivative with respect to x of this dependent variable u of x comma t. So u is a function of both x and t, and then plus t squared times dou u by dou t. So it's just the first order derivative which appears here is equal to some function involving both x and t, right? So we see that indeed the highest order derivative which appears here is with respect to x, and it's of order 2. Therefore this is a second order partial differential equations. So we will concentrate on second order PDEs, and in particular we will specialize into certain very well studied kinds of partial differential equations. But before we do that, we have this sort of broad classification of second order PDEs, and we will talk about what is called a canonical form. And so we will break these into three different classes, and so special treatments of each of these kinds will then follow, right? So in general, partial differential equation solving PDEs is a hard problem, right? So particularly if you have to put in boundary conditions, there's a whole machinery associated with the solution of PDEs, right? So we'll start our discussion with some sort of broad ideas, and so there is this transformation possible. So we will discuss these transformations and come up with what is called a characteristic equation, right? So which is all within this umbrella of classification of these second order PDEs. Once we have done this sort of a broad level discussion, we will also go into the machinery of how to solve some PDEs which appear in specific physics problems. So that's coming up later. So let us consider this sort of general second order PDE involving two variables, x and y, right? So u is a function of both x and y. I have not explicitly written u of x comma y in order to keep not clutter this equation too much. So I have a times dou squared u by dou x squared plus b times dou squared u by dou x dou y plus c dou squared u by dou y squared plus d dou u by dou x plus e dou u by dou y plus f u equal to g. So this is a very general second order PDE involving two variables, right? So in real world applications, sometimes it's useful to consider, you know, 3 variables or even 4, right? So 4 variables is the general problem involving 4 variables already becomes quite complicated, but up to 2 and 3, so there is this sort of general framework which is possible to write down, and there is this canonical form and so on, it can be done. So but from our point of view, we'll just stick to the 2 variable version. So second order PDEs, and where the dependent variable is a function of 2 independent variables, and I'm calling them x and y. So these coefficients a, b, c, d, e, f and g are all in general functions of both x and y, right? So now if we consider a, you know, generic PDE of this form, it's possible to classify into 3 types based on the relationship between a, b and c, right? It turns out that these other, you know, terms, you know, don't really feature in this classification, right? It's only about a, b and c. So you sort of think of this as a like a quadratic form, and then you study the nature of the so-called discriminant, right? So you will see in a moment how this appears, right, when we further look at some transformations. So the idea behind classifying these differential equations into these 3 different boxes has to do with a useful transformation which can bring these differential equations into a canonical form, and this canonical form will actually depend only on these 3 terms. The others also will undergo some changes, but really the focus is on a, b and c. So you define this discriminant delta, which is given by b squared minus 4ac. You can think of it like a sort of a quadratic equation, will also come in explicitly, but this is like a quadratic form. So discriminant delta made up of b squared and 4ac in similar, b squared minus 4ac. Depending upon the value of this discriminant delta, there are these 3 different types possible. So if delta is less than 0, if b squared minus 4ac turns out to be less than 0, then we say that the PDE is of the elliptic type. If delta equal to 0, that is if b squared happens to be equal to 4ac, then we say that this is of the parabolic type, and if delta is greater than 0, we say that the partial differential equation is of the hyperbolic type. So that is b squared is greater than 4ac. Now of course I said a, b, c can all in general be functions of x and y. So indeed, so the type of the differential equation itself can vary as a function of x and y, right? So we will, you know, primarily look at PDEs whose type remains the same in the entire domain in which these independent variables are defined. But in general, it is of course true that, you know, a differential equation could be elliptic in one region but hyperbolic in some other region, and parabolic in a third region, and so on, right? So this quantity delta is really computed at the point x comma y, right? So we will see that there are examples or, you know, generic classes where the value of delta is the same for all values of x comma y, or its sign is the same, right? It's all about the sign, whether it's positive, negative or 0. Okay, so let's look at the idea of a canonical form. So the idea is that once you have figured out the type based on, you know, a, b and c, you can transform this differential equation, this partial differential equation into another partial differential equation, you know, where you basically make a change of variable, right? So what we do is, you know, consider 2 new variables and recast this PDE into another PDE which is in a canonical form, right? So what is this canonical form? We will discuss ahead. So the idea is that you rewrite this differential equation in terms of 2 new variables, zeta and eta. Both zeta and eta are functions of x comma y, right? So we have the freedom to choose these 2 functions, and indeed we must choose these variables in such a way that this Jacobian is non-zero, right? So that basically means that this zeta and eta are independent. You cannot take zeta and eta to be some factor of zeta, for example. Then it's not going. You're not going to be able to compress information which has two independent variables in terms of just one independent variable. That is not happening, right? So this Jacobian being non-zero ensures that zeta and eta are valid two new independent variables in terms of which the whole partial differential equation can be recast into a form which is more convenient to work with, right? So the idea is, so now it's a matter of sort of cranking this machinery. So there is this chain rule using which we can write all these partial derivatives in terms of the new variables. So dou u by dou x must be written in terms of dou u by dou zeta, and then dou zeta by dou x plus dou u by dou eta times dou eta by dou x. And similarly you will have a relation for dou u by dou y. So now when we take the second order derivative, dou squared u by dou x squared will get you dou squared u by dou z squared, and so then you get a dou z by dou x times dou z by dou x, that is going to give you the square. And then when you take a derivative with respect to dou squared u by dou z zeta dou eta, then you get a dou zeta by dou x times dou eta by dou x, and likewise you will get a similar cross term from the other one, and so you get a factor of 2. And then of course you have dou squared u by dou eta squared times dou eta by dou x times dou eta by dou x. So this is when the first three terms come about when when you take this derivative with respect to dou x, considering dou u by dou zeta, you're taking a derivative with respect to this part. But then there are also two more terms which come about where you treat this dou u by dou zeta as basically a constant. So when you're taking a derivative with respect to x, then you get a dou squared zeta by dou x squared, and likewise you have a dou squared eta by dou x squared term. So, well, I mean, you have a similar relation, slightly different. You have to take care of these terms. Instead of a factor of 2, you get these two different terms, right? When you take a derivative with respect to dou x and dou y. So it's like double derivative, but with both x and y in the with respect to which the derivatives are taken. So you can convince yourself that indeed this is the expression you get, right? It's just a matter of taking this dou u by dou x and taking a derivative with respect to dou by dou y, or equivalently you can take dou u by dou y and take a derivative with respect to dou x. Both are going to give you the same answer. And then dou squared u by dou y squared is going to be similar to dou squared u by dou x squared. So in place of x you put in y. So these are all like very general, this is a completely general result. So you're given some u, you can take a derivative with respect to x and with respect to y and second order derivatives and so on, and they all will be written in terms of this new variables. Now, so what this will do is, if you can plug in, so wherever you have, so you go back to this original PDE, and then wherever you have dou squared u by dou x squared, you must rewrite it in terms of this expansion. So basically what it will do is, you can check this, it will basically give back another partial differential equation in terms of zetas and etas, right? So it's going to look like this, where these new coefficients are connected to the old coefficients in terms of these relations. I will allow you to check this. So for example, a is just a times dou zeta by dou x squared. So we can look at this. So if I look at dou squared u by dou zeta squared, for example, it comes here. So there is one term like this, dou zeta by dou x the whole squared. So that also appears here. So because there is a factor of a, and then where else does dou squared by dou zeta squared appear? It appears in this term here. So then you have a dou zeta by dou x times dou zeta by dou y, and indeed that appears here. There is a factor of b associated with this term, and then indeed there is also plus c times dou zeta by dou y the whole square. So indeed, so a, which is the factor that you tag along with dou squared u by dou zeta squared, comes in these three different forms. You can check this, right? And likewise, we can work out B in terms of all these partial derivatives, C in terms of all these partial derivatives, D again, and E, and F and G are basically these last two terms. So you see that you have F acting on U, small f acting on U will become capital F acting on U, and small g acting on G will become capital G acting on U. That's the stuff which appears on the right hand side. So basically you can rewrite this PDE in terms of a new PDE, and it's going to look like here. And now, so the key point is that because we can show that B squared minus 4AC. So you have a partial differential equation, again a second order partial differential equation. You have a new A, B, and C. So I said that it's only A, B, and C which count as far as the type is concerned. And so this transformation leaves this type invariant, right? So that we can see because it's possible to show. So this is going to be exercise. You must show this using all these relations that the discriminant of this new partial differential equation, B squared minus 4AC, capital B squared minus 4 times capital A times capital C, is related to the old discriminant by this expression. So there is this factor squared times B squared minus 4AC. Now since there is a square here, which means that it's going to be a positive number. So therefore the sign of this is unchanged. If this is negative, this is also going to be negative, and if this is positive, then this is also going to be positive, and if B squared is equal to 4AC, of course capital B squared minus 4AC also is going to be 0. Therefore, I mean that comes about from because this Jacobian has been chosen to be non-zero. If this were 0, of course, then you may take a positive number and take it to be 0. So the Jacobian being non-zero, we said, is a requirement because this new variable zeta and eta are independent. Therefore, the non-zero nature of the Jacobian ensures that the type of this differential equation is unchanged under this transformation. Now, based on based on which type the equation is, based on the value of this discriminant delta, if you go back and make this transformation, right? So there is full control over zeta and eta. So we will go into these details in the lectures to follow. So the point is that there is a way to choose this zeta and eta, right? We have full control on zeta and eta. You can choose your zeta and eta such that if it is a hyperbolic differential equation, you start with this complicated looking differential equation, but you can rewrite this in this form, right? Dou squared u by dou zeta squared minus dou squared u by dou eta squared is some function of all this stuff, zeta, eta, u, dou u by dou zeta, whatever needs to come can come on the right hand side in terms of all these arguments can come into this function. But the key point is that the second order derivative with respect to u of u with respect to zeta and of u with respect to eta, the sign associated with these two terms are opposite. Or you can equally write this resulting differential equation as the second order derivative with respect to zeta and eta as some function, right? So we will see an example, we will see exactly how this happens, right? So this is one form, this is one possibility. If it's a hyperbolic partial differential equation, it can be written in this manner, from which it becomes, it's simpler to handle this canonical form, right? Sometimes it's possible to use the canonical form and immediately write down the solution, but sometimes even with the canonical form there is still some more work to do. But the key point is that if you can bring it to the canonical form, then we can develop techniques for the canonical form itself, and so that's where the power of this classification lies. Now if it's of a parabolic kind, so delta equal to b squared minus 4ac, we can recast this PD in one of these forms. Dou squared u by dou zeta squared itself will be a function of this stuff. Equivalently, you may be able to write it as dou squared u by dou eta squared. It doesn't matter which variable. It's really, these two are in some sense really the same, because you can there's no hard and fast rule about which variable you call zeta and which you call eta. So there is a way to cast it either in this form or in this form, and then there is the elliptic form, so which is where the sign of the second order derivative with respect to zeta and the sign of the second order derivative with respect to eta are the same. So dou squared u by dou zeta squared plus dou squared u by dou eta squared is it can be a complicated function of zeta, eta, u, dou u by dou zeta and dou u by dou eta, right? So this depends on the specific problem at hand. right? So this the key point is that you can take a partial differential equation of this generic type, and there exists a transformation, as we will see. We will show explicitly how to do this, which can bring it to one of these three canonical forms, right? So there is some some details about how you can write it in this manner or in this manner if it's a hyperbolic PDE, and again in this manner or in this manner if it is a parabolic type, and there is one sort of generic type if it's an elliptic type of differential equation. But really, there is a way to sort of think of these interchangeably. So that's why this is the canonical form for hyperbolic differential equations, this is for parabolic, and this is for elliptic. So we will go over this again in detail in the lectures ahead. That's all for this lecture. Thank you.